So first of all, as I know that some of you have been to the domain decomposition conference 2 weeks ago, so if you happen to be at my talk, I talked about the same topic and there hasn't been that much of apologies. Yeah, so Martin already pitched my talk very nicely. I think I
Oh, you have a laser point.
Mario and I are the reduced basis guys in this collaboration. So I will start saying a few words about reduced basis methods and how I got interested in this topic from that perspective. So here is the standard reduced basis method in a nutshell for the classical application of elliptic problems. So here we have an elliptic problem in weak formulation. A is the bilinear form and F the right-hand side functional. UH is the solution. And the problem is parametrized. Yeah, so the mu here is a parameter. Everything depends upon that. And then this would be my full order model, yeah, finite element discretization. Maybe I could also formulate this in the analytical setting, but in practice it has to be a discrete formulation, so very high dimensional finite element space. And now I want to solve this problem quickly for many parameters, and doing this with the finite element model is just too expensive. So I want to have a reduced order model for that. And what I do in reduced basis methods is super simple. I just pick a smaller space, do Galerkin projection onto the smaller space, and I have my reduced order model. Yeah, and the promise of reduced basis methods is that while the finite element space has maybe millions of degrees of freedom, the dimension of our reduced space will be like 10 or 100. Yeah? And this can work if the solution depends smoothly on the parameter. Yeah? So this is what we exploit to find a good approximation space for all the solutions for all parameters. Yeah? And in many cases, like for elliptic problems, this is usually satisfied. Yeah? And now the question is, how can we find such a reduced space? And we do this by actually solving the full order model for some parameters and then just taking the linear span of these solution vectors we call snapshots. Yeah? And the parameters for which we solve are usually selected in a greedy manner. So we have such a greedy loop where we start with a zero-dimensional space maybe. Then we estimate the model order reduction with a cheaply evaluable error estimator, select the parameter for which the error is the largest, compute a full order model solution snapshot, put it in the reduced space, and rinse and repeat until we've converged. Yeah? So there's more to the story, of course, but here is some real world application. Yeah? So this is now nonlinear, time dependent, yes, a microscale battery model. We've looked at roughly 3 million degrees of freedom, one simulation, one snapshot, 15 hours, reduced order model for that 8 minutes. Yeah, so if RB method works, then it is like that. And
the parameter here?
Discharge rate. And yeah, part of this project here, outcome of this was also a very nice software, Pymo, which is open source. And if you can integrate it into your own project, if you're interested, come talk to me. Yeah, but there are some caveats. In particular, you have this offline phase where you have to solve the full order model. And of course, this takes time. After that, everything is for free. Yeah, but if you have a high dimensional parameter space, then your dimension of the reduced space will increase, and this can get very expensive. Yeah? And then the question is how you want to deal with that. Yeah? For everything, you can't maybe find a solution, but what we are in particular interested in, if we have many parameters which are somehow local in space, yeah? And if I change them, maybe the effect is also only local. And if I look at something like this, yeah, then an obvious idea is to do localized model order reduction. Yeah, so I take a domain decomposition of my computational domain, and then I build reduced spaces on each of these subdomains. And and my goal is to build these spaces only by solving small local problems, not on the entire domain. And other things have been obviously done in domain decomposition and multiscale methods, and we do something quite similar. So we take a domain and then we enlarge this domain to a so-called oversampling domain, and then we prescribe some boundary conditions we don't really know on the oversampling domain, but for an elliptic problems, at least the high frequency parts of the error will go away if I move away from the boundary, and so I can get good approximation spaces locally. And then I somehow have to couple this, and there are various approaches to do that. But let's talk about time. And there the situation is quite similar. If I would do standard reduced spaces methods, I would have to compute solution snapshots for the whole time domain. And now I also want to somehow localize this. And this leads us formally to what we would call the transfer operator in time, which is simply doing the following thing. So I start at a point in time Tn, and I prescribe initial values. This is the input to my operator. And then it computes the solution at a future point in time Tn plus 1. And the solution is then the evaluation of my operator. And now it's quite easy to see that for linear parabolic problems, this transfer operator is affine and its linear part is compact. And then I can, if I have a compact operator and I want to approximate this operator, what I do is singular value decomposition. And a method out of this has been done by my colleague Julia Schleus, also from Münster. And what they did is they pick some points in time, T1, T3, T5 here in this picture. And then they put some random initial conditions at these points, evaluate the transfer operator, and then they look at what remains at the future point. Right? And what remains, they put in the global reduced space and then project onto this reduced space. And then there are some heuristics to select these points in time based on the data in the equation. But this gives us one fixed reduced space for all times. So it's not really local in time, and there is also no iterative approach to that to convert to machine precision. And this is where Parareal enters the picture, because this transfer function operator in time in Parareal would be simply my fine solver. So I make no difference between the analytical solution and the fine solver here. So the fine solver is what we would call in model order reduction the truth solution. It's good enough for us at least. And then I have my coarse solver. So Fn is the evaluation of the fine solver at time n, and Gn the coarse solver. And here is my standard Parareal update formula. I do initialization where I go through the time domain once with the coarse solver. Then I have the Parareal update here where I evaluate the fine solver in parallel all time domains, and then I step the time of the coarse solver with this course correction. Okay, and this is basically what Martin has shown you before. If we look at the heat equation and some arbitrary source term, and we run Parareal on this, and we use Dirichlet boundary conditions, then this Parareal works actually with no coarse propagator at all. So here you see the error over time, spatial error over time, and each color is one iteration of Parareal. The error goes down, albeit not very quickly. And as Martin already hinted at, you can quantify this also exactly for this problem by doing some Fourier analysis and write down the solution exactly. So here UM hat are the Fourier coefficients of the solution over time. And here you have the Fourier conditions, coefficients of the initial data. Yeah, and here you have your exponential decaying term here time. And then have the inhomogeneous part. Yeah? And now if we want to improve, what makes sense is to include a few of these Fourier modes in my coarse solver. Yeah, so I just take here, I ignore the inhomogeneous part here and define as coarse solver, take the Fourier coefficients of the initial data and propagate them as you know they will propagate over time. And if you run Parareal with this, then the errors look like that. Yeah, so for instance, here, if you include just 3 Fourier modes in your coarse solver, then so here is no iteration. Here is the first Parareal update. Here is the second, and after 3, you're down to machine precision. Yeah, so this converges really super quickly. And yeah, you can make this analysis a bit more general for arbitrary self-adjoint line solvers. Yeah, and then you get here this linear convergence rate where the rate is given by the first neglected eigenvalue of your fine solver. Yeah, but in reality, we not always solve the heat equation on a line. So maybe we don't know these Fourier modes a priori for or the evolution of the Fourier modes a priori. So we want to extend this to a more general case. Yeah, so the general case is the following. We have an arbitrary Hilbert space V, and for each time interval, a fine solver Fn, which I assume to be linear affine with a compact linear part. Yeah, and this on the analytical level would be the case if I looking at a linear parabolic PDE with time varying coefficients. And also if I go to the discrete case for a nice discretization, the Fn will still be affine linear. If not, we assume it's almost as good as solving analytically, so it's almost affine. So this is not really a restriction for the algorithm. So here the Fn prime is the linear part and the Bn will be the affine component of the fine solver. And in particular, being compact, the fine solver linear part has a singular value decomposition. I write down like that in coordinate-free form. Yeah, so I take here the inner, so V is my input, and I take the inner products with the right singular vectors, scale by the singular value, and then I multiply with the corresponding left singular. And now my spectral or reduced basis coarse solver, however you want to call it, is simply given by a truncated SVD of the linear part of the fine solver. And I also include the affine shift. As Martin already said, in each Parareal update, the affine part cancels out anyway, but for the initialization, it matters. And as we will see in a second, it's basically for free to also include that in our algorithm. And if we do it like that, we already have a bound on the error how good our coarse propagator is. Yeah, it's just the first neglected singular value of the fine solver. Yeah, and now the question is, how can we compute this SVD? And in practice, it will not be a good option to evaluate this fine solver on every finite element degree of freedom. So we need a more suitable method for that, which is randomized singular value decomposition. I show here on one slide. I mean, there's an entire community behind this. This is the basic algorithm. You pick, so if Rn is your desired truncation rank, you pick Rn plus some more, this star more is P, which is also called oversampling. So I pick Rn plus P random vectors, and then I evaluate my operator I want to compute the SVD of. So here my fine solver on these random vectors. And I look at the span of all these random vectors and I compute an orthonormal basis for that. And then I apply the adjoint operator to these orthonormal basis vectors. And of that I call X. And then I also compute an orthonormal basis for this X space. And now the idea is that I approximate my operator by taking the operator and then projecting on this approximate range W. And then there is stochastics for this telling you that this will actually be a good approximation for the range of the operator, depending on the singular value decay of the operator. And if you do this approximation and then basically expand everything in this V and W basis, you end up with this, where here in the middle you have a small dimensional matrix. You then compute the SVD of and take the right and left singular values vectors of this matrix SVD and form a linear combination with these basis vectors here, and then you have the randomized SVD of the operator. Yeah, so relative computationally very simple approach. Yeah, so you basically have to do these fine solver evaluations and the adjoint evaluations, and you can do all these in parallel. Yeah, so this is all embarrassingly parallel. You first have to do the Fn evaluations and then the Fn star evaluations. As I have been asked before, there are also single shot methods where you can evaluate Fn and Fn star in parallel. So you can also do all these evaluations in parallel. Yeah? And if your truncation rank is Rn, then you have Rn plus P plus 1. So the 1 is here for the affine part, evaluations of the fine solver. And then you have Rn plus P evaluations of the adjoint, and that's it. Yeah, a bit of linear algebra, but this is cheap compared to the evaluations of the fine solver. And then you can do error analysis for Parareal with this Coarse solver, and you get out the standard Parareal estimates you might know if you know the theory. Yeah, so in particular, you have this superlinear convergence bound, where here you have epsilon to the k. So epsilon is the truncation error. And here you have powers of delta. Delta is the norm of the fine solver, or the first singular value of the fine solver. Yeah, so epsilon is supposed to be a small number, so this goes down. And then here these binomial coefficients, if the m increases, also go down to 0. So this is why it's superlinear. If you assume, in addition, that the delta is smaller than 1, then you can form sums, and then you get this linear convergence bound, which holds for all times independent of the number of time intervals. And one nice thing here is that this is actually computable, because after you have run the initialization phase, you actually know epsilon and delta. So you can really evaluate it, and then you see that it's much larger than the actual error, because it's just a very rough a priori estimate. But you can do that. And as promised by Martin, is here a slightly sophisticated academic example. Yeah, so this is still on one machine, but it has at least 400,000 degrees of freedom. So we look here at this heat sink geometry. We have heat influx from below, and then at the fins you have the boundary conditions which change over time. Yeah, so which makes this equation time dependent both in the affine and in the linear part. And yeah, so then we run Parareal on this with our spectral Coarse solver and compare it again to this one-step Euler Coarse solver. Here, the black dashed line is the convergence of the Euler variant. And here, even with a zero-dimensional Coarse approximation, we again converge much faster. And then by taking, let's say, 3 singular vectors into account, we end up here after 4 iterations, we are at machine precision. And so in this case, it's actually true that if you count the fine solver evaluations you have in the training phase for the Coarse solver and then the Parareal updates, you actually need less fine solver evaluations than for the Euler single-step Euler method, because it converges so much faster. Yeah, so this is one nice thing here, but in addition, you have much more parallelism, yeah, because most of your fine solver evaluations are in this training phase of the problem where everything is embarrassingly parallel. And at the same time, you solve linear systems with multiple right-hand side as you are stepping through time. Yeah, so you can also exploit Bloch-Krylov methods, SIMD, and whatnot. Yeah, so I think this can, for this class of problems, really make this quite attractive. And one final thing is, yes, we saw the a priori estimates didn't really work, but we also have a posteriori error estimates, which are also easily computable. Yeah, so they only depend on epsilon and delta and the update. Yeah, so you really don't have to do any significant additional work to evaluate these error estimators. And here I've plotted the efficiency of the error estimator. So true error divided by estimated error. So this should stay below 1, and it does. So here the dashed parts is where we are already at machine precision anyway. So don't look at that. Everywhere else we are below 1. In some cases, the efficiency is not very good, but this is due to the fact that the algorithm converges so fast. Yeah, so if you have one step where you get to an error of 0, then you would still have here an update, but the actual error is just 0. And if you look at it, then you can see that if you use this as a stopping criterion, then you will have maybe one more iteration than actually necessary. Yeah, so this can be also quite useful in practice. So that's all I wanted to say today. Martin already mentioned our preprint, which includes some of the ideas, and the full paper is still missing an introduction, but is ready otherwise. And you can find the slides of this here. Thank you very much.